Hello everyone, listening Radio Khanchi 90.4 FM, हम सबका रेडियो. I am Dr. Rajiv Asthana, Associate Professor, Gossamer College, Ranchi. Today I will discuss Stark effect, which is in second semester of PG course, Ranchi University. The influence of an external electric field on atomic spectra was discovered by Stark in 1913 and is known as Stark effect. If the energy levels shift by an amount proportional to the electric field strength, then it is called linear Stark effect. Stark's discovery was made on the Balmer series of hydrogen. The theory of Stark effect in hydrogen was the first application of the perturbation theory in quantum mechanics. If the energy levels shift by an amount proportional to the square of the electric field, then it is called quadratic Stark effect. The Stark effect is responsible for the pressure broadening, that is Stark broadening, of spectral lines by the charged particles. When the split or shifted lines appear in absorption, the effect is called the inverse Stark effect. The Stark effect is the electric analog of the Zeeman effect, where a spectral line is split into several components due to the presence of a magnetic field. Linear Stark effect depends crucially on the degeneracy of the 2s and 2p states. This degeneracy is a special property of a pure Coulomb potential and therefore only applies to a hydrogen atom. Thus, alkali metal atoms do not exhibit the linear Stark effect. The main features of the phenomena are: number 1. All hydrogen lines form symmetrical patterns, but the pattern depends markedly on the quantum numbers n of the terms involved. The number of lines and the total width of the pattern increases with n. Second, the wave number differences are integral multiples of a unit, which is proportional to the field strength and is same for all hydrogen lines. Third, certain components appear only in transverse observation and are polarized with the electric vector parallel to the field, called pi components. The other components, called sigma components, appear polarized with the electric vector in the xy plane in transverse observation and unpolarized in the longitudinal observation. Except for the absence of circular polarization, the polarization properties thus resembles those in the Zeeman effect, but in contrast to the latter, the pi components show greater shifts than the sigma components. In this slide, Stark effect patterns are shown for the first 4 Balmer lines. The theoretical relative strengths of the components of each line are shown by the lengths of the bars, with very weak components indicated by half circles. The cross marks indicate the measured relative intensities of certain components of the same polarization. In this slide we can see the energy term diagram for the linear Stark effect. Now we look into the wave mechanical treatment of linear Stark effect. In Cartesian coordinates x, y, z, the Hamiltonian for an electron having reduced mass mu charge minus e in a hydrogen atom in an external electric field capital E in the z direction is given by, in Gaussian units, h is equal to p square upon 2 mu minus e square upon r plus small e capital E z. This is equation 1, where p square is equal to px square plus py square plus pz square. Px, py, pz are the momenta conjugate to the coordinates x, y and z. The parabolic coordinates xi, eta, phi are related to x, y, z, given as z is equal to xi minus eta upon 2, x plus iy is equal to square root xi eta into e to the power I phi. This is equation 2. From equation 2 we can get r square is equal to x square plus y square plus z square equals xi eta plus within bracket xi square minus 2 xi eta plus eta square divided by 4 equals xi plus eta whole square upon 4. This is equation 3. The we get r is equal to xi plus eta upon 2. This is equation 4. The following figure shows what Epstein calls a meridian plane, a plane through the z-axis as the electron orbits the nucleus. Within this plane, the electron stays between xi minimum and xi maximum. In parabolic coordinates, the Hamiltonian in equation 1 is given by h is equal to 1 upon 2 mu within bracket 4 upon xi plus eta p psi xi p xi plus 4 upon xi plus eta p eta eta p eta plus 1 upon xi eta p phi square bracket closed minus 2e square upon xi plus eta plus 1 upon 2 small e capital E into xi minus eta. This is equation 5, where p xi, p eta, p phi are the momenta conjugate to xi eta phi. Now we substitute p xi as h cross over I del over del psi, p eta as h cross over I del over del eta, p phi as h cross over I del over del phi. This is equation 6. To form the Hamiltonian operator of time independent Schrodinger equation, h psi is equal to alpha 1 psi. Equation 7, where psi is in the parabolic coordinates, alpha 1 is the eigenvalue of the energy. Now using equation 6 in equation 5, we will get h is equal to minus h cross square upon 2 mu within bracket 4 upon xi plus eta into del over del xi, xi del over del xi plus 4 upon xi plus eta del over del eta, eta del over del eta plus 1 upon xi eta del square over del phi square bracket closed minus 2e square upon xi plus eta plus half e into xi minus eta. Equation number 8. Now inserting this Hamiltonian operator in equation 7, dividing both sides by psi and multiplying by 2 mu xi plus eta, we will get minus h cross square within bracket 4 del over del xi, xi del over del xi plus 4 del over del eta, eta del over del eta plus 1 upon xi plus 1 upon eta into del square over del phi square bracket closed minus 4 mu e square plus mu e into xi square minus eta square is equal to 2 mu xi plus eta into alpha 1. This is equation 9. The solution of equation 9 can be written in variable separable form as psi function of xi eta phi is equal to psi function of xi, psi function of eta, psi function of phi. Equation 10, where psi function of xi is e to the power I s xi upon h cross, xi eta is equal to e to the power I s eta upon h cross, psi phi is equal to e to the power I s phi upon h cross. As we could set s function of phi is equal to alpha 3 phi, we can set psi as a function of phi is equal to e to the power I alpha 3 psi upon h cross, with alpha 3 is equal to mh cross. After substituting minus m square psi for del square over del phi square in equation 9, we get an equation that splits into a part that only depends on psi and a part that only depends on eta. The two parts must each be equal to constant. Denoting these constants minus alpha 2 and plus alpha 2, we get minus 4h cross square upon psi d over d xi of xi d psi over d xi plus m square h cross square upon xi minus 2 mu e square plus mu e capital E xi square minus 2 mu alpha 1 xi is equal to minus 2 alpha 2. Equation 12. Minus 4 h cross square over xi d over d eta of eta d xi over d eta plus m square h cross square over eta minus 2 mu e square plus mu e capital E eta square minus 2 mu alpha 1 eta is equal to plus 2 alpha 2. Equation 13. The last two equations can be rewritten as xi d2 psi over d xi square plus d psi over d xi plus 1 upon 4 bracket start 2 mu e square over h cross square minus 2 alpha 2 over h cross square minus m square over xi plus 2 mu alpha 1 over h cross square xi minus mu e capital E upon h cross square xi square bracket closed psi is equal to 0. Equation 14. Eta d2 xi over d eta square plus d psi over d eta plus 1 upon 4 bracket start 2 mu e square over h cross square plus 2 alpha 2 over h cross square minus m square over eta plus 2 mu alpha 1 over h cross square into eta minus mu e capital E upon h cross square eta square bracket close psi is equal to 0. This is equation 15. We now solve equation 14 for psi as a function of xi for the case E is equal to 0. It will be convenient to introduce a quantity n as na equals h cross over square root minus 2 mu alpha 1. Question 16, where a represents Bohr radius, that is equal to h cross square over mu e square, and alpha 1 is equal to minus h cross square over 2 mu a square n square. So equation 14 for e is equal to 0 can be rewritten as xi d2 psi over d xi square plus d psi over d xi plus 1 upon 4 bracket start 2 upon a minus 2 alpha 2 upon h cross square minus m square over xi minus xi over n square a square bracket close psi is equal to 0. Equation 17. Here psi can be written as psi is equal to xi to the power m by 2 e to the power minus xi over 2na f function of xi. Equation 18. We then derive an equation for f function of xi. The solution of this equation will be a polynomial summation ck xi to the power k that will break off if and only if there is a value n for k such that n xi is equal to n upon 2 bracket start 1 plus m plus 1 upon n bracket closed minus alpha 2 na over 2h cross square. Equation 19. In the similar way for equation 15 we will get n eta is equal to n upon 2 1 minus m plus 1 upon n bracket closed minus alpha 2 na over 2h cross square. Equation 20. From equation 19 and equation 20 we will get n upon 2 bracket 1 minus m plus 1 upon n bracket closed minus n xi is equal to n eta minus n upon 2 bracket start 1 minus m plus 1 by n bracket closed. On simplification we get n is equal to n xi plus n eta plus m plus 1. Equation 21. Comparing this result in wave mechanics with the corresponding result in the old quantum theory, n is equal to n xi plus n eta plus m, we notice that the difference between the two is of the final term plus 1. This extra term eliminates the need for a special condition to rule out m is equal to 0. The power series solution of psi function of xi and psi function of eta turn out to be Laguerre polynomials. The full normalized energy eigenfunction solutions for the state characterized by quantum numbers n xi n eta m with principal quantum number n is equal to n xi plus n eta plus m plus 1 in the unperturbed case, that is a hydrogen atom in zero electric field, take the form psi function of n xi n eta m is equal to c function of n xi n eta m into xi over na to the power m by 2 into e to the power minus xi over 2 na into eta upon na to the power m by 2 into e to the power minus eta upon 2na into L mn xi of xi over na into L mn eta of eta over na into e to the power I m phi, where C n xi n eta m is called normalization constant. Introducing the Stark perturbation operator, H Stark is equal to 1 by 2 small e capital E into xi minus eta. The standard procedure of first order degenerate perturbation theory instructs us to calculate the matrix of the perturbing operator in the basis of the n square degenerate states of identical unperturbed energy corresponding to a given principal quantum number n. The calculation using standard properties of Laguerre function gives the perturbation matrix as equal to 3 upon 2 small e capital E n bracket n xi minus n eta into a into delta n dash xi n xi into delta n dash eta n eta into delta m dash m. The perturbation matrix is in fact diagonal in this basis, so the Stark energy shifts can be read off directly. So here I conclude my discussion on linear Stark effect. Thank you for listening it. Thanks.